Do we have to do the beam steering from UE side? Both at it cover, does that lecture, that slide covers both initial access and also beam tracking? Meaning that even at beam tracking time, we also have to look at the UE beams and find the best beam at each time frame somehow.
Yeah, I guess that's up to the UE implementation, so to say, to pick the best reception beam. And then the transmission beams, that basically follows what we talked about before lunch.
Okay.
I'm not sure that was a complete answer to your question, but I missed the first part of the question. It was a bit noisy, but.
Change position.
Okay, share my screen. This was. Yeah, that's the third part. Okay, so is everyone back from lunch?
Yes.
Yeah, good.
Oh, wait.
Hope you can see even more high-tech stuff on the screen now.
Also one question, Stefan. So
yeah.
with all the question that was made before, how do you deal when there are multiple users? Do you have to do like some organization of the beams or something like that, or do you treat it normally, or there is any standard for that?
I mean, typically, one UE is not aware about what another UE is doing.
Yes.
I would say that the baseline thing is that you schedule different users on different time frequency resources. So either at different points of time or different frequency parts or combination of. You can, of course, schedule two users on the same time frequency resource if they are spatially separated to something. Now that's up to the base station to take that. And then you try to pair two UEs that are fairly orthogonal in the spatial domain and transmit to those two.
So in the scenario that all the users would be clustered nearby, so if they are together more or less, and there are many users, it would be still not likely to separate the users, right? So there would still be noise.
Yeah, if you have two users that are standing very close to each other, then they probably have more or less the same radio channel, and then it's probably difficult to try to address them at the same time. Then you split them in time domain with different of them symbols or different resource blocks or something. So, and I mean, multi-user MIMO, that is a way to increase the capacity. When you run out of time frequency resources, you can start to put users on top of each other if the channels are good enough. The tricky thing is, of course, to find two users that at the same time have data awaiting transmission and have an orthogonal radio channel. It is a little bit tough, that part of it. And one should remember that most of the time, I think like 80% of the time, the base station is not transmitting anything, even at a very high load. Because packet data is burst and you don't have data to all users all the time and so on, depending on what application they run.
Okay.
So sometimes when you compare different algorithms, people use full buffer. They have an infinite amount of data waiting for each of the users, and they show something. And sure, that's the first step of getting some insight into what's happening. So that's fine. But one should not forget to also look at what happens when I put some more realistic traffic models on top of this, that users download web pages and then they browse the page for a while before they click something, or whatever video streaming, it might be a little bit burst and whatever it could be. So in many cases, many of these gains that you can show with full buffer, they disappear when you put more realistic traffic models on top of it.
Okay, thanks.
Okay, so let's talk a little bit about scheduling and retransmission, and actually also a little bit power control and timing advance to start with as part of this, for about an hour or so before we take a break. So I hope you remember before lunch we talked about the transport channel processing. We looked a little bit about reference signals, and we talked about multi-antenna handling, how we can do pre-coding and in the uplink both codebook based and non-codebook based. So scheduling retransmissions and so on. But let's start with timing advance and uplink power control, just to complete the picture. I don't have much to say, but basic slide on each, but to make sure that you cover that part as well, so what's going on there. Since NR is a scheduled system, and you want to schedule different users such that they are orthogonal, that they transmit at different points in time or in different frequencies, you need to both, of course, control the carrier frequency in the UE so that they have the right frequency. And that the devices can do by themselves. They check the downlink, the frequency of downlink carrier they're connected to, and then lock their oscillators to that. So that's fine. But then you also need to control the uplink timing somehow. And if you want the devices to be orthogonal in the time domain at the base station, then the uplink transmissions must be time aligned at the base stations. And that of course means that a UE, that is a device that's close to the base station, need to start the transmission a little bit before the downlink, so to say. The subframe start of the uplink or the slot start of the uplink needs to be a little bit earlier than the downlink, because the uplink is due to the propagation layer over there. It arrives aligned with everything at the base station. And if you have a device that is further away, of course, then you need to advance the timing even more, because the propagation delay is great for that UE. So then you apply a larger timing advance to make sure that they are aligned time-wise at the base station. So the way you do that when you're up and running is that you measure the timing of each of the different UEs. You can measure on the ongoing data transmission, or you can configure the UEs to send the sounding reference signal or whatever. You measure that, you estimate the timing error, and then you send a command to the device how much it should advance or retard its uplink timing, such that you're aligned at the base station. And this type of timing advance commands, you send them maybe once or twice per second or something like that. It's relatively infrequent because they don't change more than that. And then you basically have aligned all the uplink transmissions at the base station, and also with the downlink. So that is timing advance. And this is something that it's been used ever since DSM. So it's nothing new in principle as such. But
what is the accuracy that you are trying for?
I mean, you should be within a fraction of a cycle prefix, that range.
So it basically means that when you go for the higher frequency variant like frequency range 2, you are really have a kind of rather tight timing advance.
Yeah, then apply timing advance as well, and then the accuracy you get is fractions of a microsecond.
Yeah.
There is a table in the spec where I can see how much you can advance and retard the kind of range of this. I don't remember all the numbers by heart, but one can look it up if you need it for something. So it's a fairly accurate timing advance in that sense, but it's not complicated to do. So no magic really. The other thing you would like to control in the uplink, that's the power, transmission power. You basically want, assuming that you have the same data rate of two users, you want them to be received by roughly the same power. It's not super critical. I mean, it would probably be more critical in a CDMA system, but since we have an orthogonal system, it's a little bit less critical. But still, you have power control because you don't want to blast out too much power, because that would cause too much inter-cell interference to neighboring cells. So try to use the power you need for the data rate you're scheduling with, but not more than that. So in NR, there's a combination of open and closed loop power control. There's basically this formula out of my book. So this is a factory configured. That's basically the receive power you want. Then you have an open loop part, which is fractional path loss compensation. So this is the path loss that you can estimate from the downlink. The UE knows the transmission power of the base station, and it can measure how strong it receives the downlink transmission. And then it can figure out the path loss, and then it compensates for that. If alpha is 1, you completely compensate for path loss. If alpha is less than 1, then you just do a fractional compensation. And then you have a closed loop part, which basically is commands saying increase or decrease. That the base station sends 2 bits per scheduling grant to scheduling assignment to the device, telling it to increase the power or decrease the power. So plus minus 1 dB or not change it at all, and I think you can do plus 3 dB as well. So you fine tune the transmission power that way. So when if you move further away, you get somewhere where you're a little bit hidden, then you can bump up the power. And then you have some terms here that basically account for the data rate you use. I mean, if you use a high data rate, you need a higher power to keep EBRN not constant. So that's the task of this. And you can also do if you have beam pairs, if you have beamforming both ends, then you basically have one of these equations running for each beam pair. So this would be one equation run for that beam pair, and if you indicate to the U that you schedule the other one, then it will update the other equations for that beam pair. So then basically have a number of these power control equations, one per beam pair. That's basically the way we do power control, and it's the same way as to do it in LTE. Again, nothing magic, but a combination of open loop and closed loop power control. So then we know that. And let's take a look at scheduling. What can we do in terms of scheduling? How can we schedule the device and so on? And this figure you may recognize from one of the first slides that we have all data transmissions are scheduled, either dynamically, which is a kind of typical way, or semi-persistently. But the scheduling algorithm is not standardized. That's up to the network vendor to implement. If you want to schedule that is completely fair, or if you want to schedule that prioritizes some users, or whatever you want to do. So the algorithm run here, that's completely up to the implementation. It's not at all covered by standard. And if you do downlink scheduling for downlink transmissions, of course, you have all your data coming in, different RLC entities. You do some multiplexing here and modulation coding, you transmit it. And all that is controlled by the scheduler. So the scheduler knows how much data you have for different data flows. It takes some prioritization decision out of that. It knows the channel status for all the different UEs because it gets the CSI reports, or it can extract it from the uplink sounding or by some other means. And then it takes a decision and it configures the MAC layer to multiplex to the right data flows, select the right modulation coding scheme and the multi-antenna scheme and so on. And then it transmits one transport block to the UE. And you also have downlink control signal going down to the UE so that the UE schedule knows that it's scheduled and with what data rate and so on. And the CSI reports that's measured. We talked a little bit about that before the lunch. In the uplink, we still have a scheduler in the G-node B, or the D of the G-node B. So that is, again, the algorithm is up to the network vendor to implement whatever you want. But now all the data buffer sits in the device. So what you need to know, first you need to know that there is data in that device so that it makes sense to schedule it. Otherwise you shouldn't spend resources on it. And then you probably also want to know how much data is available in the UE, how much power does it has available? Can I use a high data rate or should I settle for a lower one? So this type of status information you get up to the scheduler. Then again, you take a decision and you send a scheduling grant down to the UE, telling the UE that you're allowed to transmit on this time frequency resource with this data rate. And if you do uplink multi-antenna transmission, maybe assign a certain pre-coding matrix W and so on. But then you have some priority, and the UE needs to know which flows to transmit from. And that is a decision taken in the UE primarily. with influence of some of the scheduling grants. But basically the base station schedules a certain device. And then to a large extent, it's up to that device to pick data from different flows, according to some rules that are standardized and that are a little bit influenced by network configuration and some parameters. But scheduling is primarily per device, so to say. And then if you use carrier aggregation, remember that we can run multiple carriers in parallel from one. Yeah.
One question. That for us physical layer people, that when you climb up in the stack, there comes these kind of strange things like some kind of a channel quality indicator. No, sorry, channel quality. It's a scale, let's say, some kind of scheduling priorities that are between the flows and so on and so forth. It was not CQI, but something like that.
Yeah. Exactly. I mean, if you look in a downlink, let's say we have two data flows. We have maybe some background web email download or something like that. And we have one video browsing stream because we're watching a YouTube video at the same time. And probably the YouTube video has a little bit higher priority than the background email synchronization. So, and that has been configured also by the core network, so that you end up with different priorities at different flows. And then the scheduler is aware that it could, in principle, prioritize this flow, the videos flow over the email background sync if you want to. So that probably makes sense. And then the scheduler also know the radio channel quality, whether we're in a fading dip or fading peak. Because if we're in a fading dip, it probably doesn't make too much sense to schedule this UE because we can't push through that much data anyway. So it's probably better to serve some other UE. But if the channel quality is good, then we can decide to schedule this user. And then we probably primarily pick data from the high priority stream. And if we have some room left, we can take some of the email background low priority stream as well. Multiplex it together and select modulation and coding scheme that is suitable for what radio channel can handle.
And now somehow UE is handling that's kind of some kind of RLC level or something like that. This priorities is handled
yes
by the UE then.
Yeah, I think there is a figure in the handout slides that I didn't plan to show. We can look at that if you want to, and time allows.
Okay.
But there are you basically schedule per UE, and then there are some rules. You basically have configured a UE with different priorities of different data flows, and then you should primarily take data from the high priority flow, at least up to a guaranteed bitrate level, some kind of, it's called something else now, but some kind of guaranteed minimum data rate. If the scheduling grants then allows you some even more data, then you can pick more from this high priority and then also from low priority. So the idea there is to at least ensure that all streams have some kind of minimum data rate when you're scheduled, and then whatever scheduling grant allows above that, you give to the high priority streams first. So there are rules like that you can configure the parameters of it from the network so that you get the desired behavior.
So for me the news here is that then there exists also a scheduler at the UE in some sense.
Yeah, I wouldn't call it scheduler, but some kind of priority handling mechanism. There's something that decides from which of these flows should we take data and how much from each of these flows. Because the base station basically just says, please go ahead, you're allowed to transmit 1000 bits. And then, of course, it's up to these parameterized rules in the UE to determine how many bits to pick from each of these flows, whether it should be 500, or 800 from this one and 200 from that one, and so on.
Okay.
So that's the general principle. And then carrier aggregation, if you remember from the first session there, that we can run multiple carriers in parallel to get higher data rates and basically run them in parallel for UE. And then these carriers, or cells that they are called in the specification, because base is seen as two cells that you receive from the same time. Either each of them can schedule themselves. So you transmit control signaling on this carrier, scheduling that carrier, and control signaling on that carrier to schedule that carrier. Or you can do cross-carrier scheduling, where you put all the control signaling on one carrier, but you send control messages controlling those other carriers from that first carrier. So you have both the possibilities. And then if you do dual connectivity, then you basically have one of these pictures per base station that do dual connectivity. So then you have a completely separate schedule for the other cell. Downlink scheduling. Again, the same figure. We have most of the information available in the base station already. So I mean, we know the buffer status here. We know the priorities that. And we get the channel state information from the device that tells you about the channel quality, the radio channel quality. And as I said, I didn't put the figure here because I was focusing more on the standard, but maybe I should have done that as well. Have you? I don't know how much you thought about channel dependent scheduling and things like that, but you could think of scheduling users in a different way. I mean, one stupid way would be some form of round robin scheduling, that you basically decide among all the users that data transmitter, give them 1 millisecond each, let them take turn, and then I just go around in that circle. That is fair in the sense that you give each user the same amount of time, but it's far from the best choice. It would be better if you can figure out and take into account the channel quality, the quality of the radio channel, so that when a user has at least relatively speaking, relatively to its own average channel quality, has a good channel, try to transmit to the user when the channel is good, and try to avoid the fading dips when that channel is not so good, and then instead transmit to someone else. Then you tend to transmit to the users when they have good radio channels, and when they have good radio channels, you can use a high data rate and pump through a lot of data. And you try to avoid the fading dips when the data rate would be low and it wouldn't make much sense to schedule that user anyway. And as long as you have a number of users with independent fading channels, you always find some user with a very good channel. You get good results for that. But there's a whole range of scheduling algorithms you can play around with there. And you do it in the time domain, but you can also do it in the frequency domain. So maybe some resource blocks are good for this user, and some other resource blocks are the best for another user. And then you schedule these two users in parallel using different parts of the carrier, for example. So that indication you get from the channel state information, which part of the channel for this GUI are in good shape right now. And you get that channel status update every 10 milliseconds or something like that, depending how you configure your system. Then you take your scheduling decision and you inform the GUI. So this is control signaling. We'll talk about that next session. And typically comes to the 1, 2 of them symbols, and then immediately after that comes the data. So by looking at this control information, the device knows what date rate it has been assigned, what transport block size, the modulation coding scheme, multi-antenna information, and so on. And so it can demodulate the data and receive it properly. So that is the baseline in Downlink. And then we have one more Downlink feature in NR, which I would say is a little bit useless the way it's designed. But anyway, Downlink preemption. And this comes back a little bit to maybe slicing or priority handling in general. Let's say that we have some blue transmission going on to device A. It was on some web browsing or file download or whatever. So we schedule that user a number of gem symbols in a row on this part of the frequency band. For some reason, we just used half of it. Then it can, of course, so happen that data comes to another device that is extremely urgent. They really need to send that in to send that to device B as soon as possible. And here it's not a problem. I can just schedule that the other device, another part of the carrier, other frequency resources, so nothing happens. But sometimes that may not be possible. So I may here need to take the decision that this is so urgent. So I take the hit that I will mess up the transmission to the device A, because I need to immediately transmit this very important piece of information to device B. So I just do that with the green transmission here and corrupts the blue device A data. So far, no problem. What will happen to device A is, of course, that these two FDM symbols, or part of them, will be trashed, so it will receive garbage here. And we can probably ask for a retransmission at a later point in time. Either of the full blue stuff or just this part of it, and that's fine. And I think that is typically what will happen if you at all have these collisions. But there is a preemption indicator that can come afterwards in the next slot or sometimes later. It could tell the UE or all the UEs what happened in this previous slot here. And then it can indicate that these three pieces of resource, it's not really resource block, it's a combination of half no FDM symbol and frequency and two FDM symbols in time in this case, was corrupted because I scheduled something else than what I initially had planned for. So that's a bit up, and they only use it for that is to tell the UE that, okay, most likely my soft buffering incremental redundancy is messed up, so I should flush it and clean that one. But that's not specified. So it's up to the device to do whatever it wants with this information. That's why I think it's a little bit less useful. So this bottom part of the slide may not be the most important thing, but it could be nice to know about. The upper part is more the baseline operation and more important. That was downlink. And as I said, the control signal for downlink typically comes immediately before the data, so it will come the FDM symbol before here for the blue data transmission. Then we have uplink scaling as well, and that is a little bit more complicated in the sense that we have the scheduler in the base station. We may know the uplink channel quality from sounding reference symbols and things like that. But we don't know anything about whether there's any data in the device, what amount of data, from what priority classes, how much power is available in the UE and things like that. That is unknown. So that piece of information, the device needs to send to the scheduler. The scheduler can take a decision, taking into account also the needs from other users, and then make a decision and tell the UE to transmit in the uplink with a certain modulation scheme, and to some extent also influencing this priority handling so that the UE picks data from the right data flows. And in this case, typically the control signal is a little bit before the data, not immediately before. I mean, if you look at the TDD system here, for example, the blue is downlink, the red is uplink. We have the control signal immediately at the beginning here, and that could be control signaling informing about downlink transmission here. But they can't really inform about uplink transmissions immediately following, because this happened to be downlink slot or downlink resource. So then we have to schedule a little bit into the future, maybe 1-2 slots into the future. Maybe also being able to schedule both of these uplink time slots from one downlink occasion, because you may have different uplink downlink asymmetries. So the uplink scheduling is typically a little bit slower than the downlink one, because it doesn't affect immediately. It may affect 1 or 2 slots later or something like that, but it's still talking a millisecond or so, so it's quite fast. And if I do full duplex like an FTD system, then I can of course have downlink signal here, scheduling that uplink slot, downlink signal again, scheduling next uplink slot, and so on. Then it's less tricky. Then a little bit about this information that you need. Assuming that you know that the device has data to transmit, we'll get back to that question in a minute. I would like to know the amount of data, the buffer status, probably also the amount of data from different priorities, because I may take different scheduling decision if it's a lot of high priority data versus if it's a lot of low priority data. So that information I want to receive. And that you get on the normal uplink data channel. You have some special MAC, they call MAC control element, but this will be the header followed by user data, another header followed by user data, a special header followed by the buffer status report, and a special header followed by the power headroom report. But this is what a typical uplink transport block would look like. And then from this buffer status report, you know which of the logical channels which of the data flows that has data to transmit and the amount of it. You also want to know the power headroom. I mean, if this is the maximum power the device can transmit with, and it's currently transmitting with this one, you know that, okay, I have a certain amount of power unused that I can use to schedule. So I could actually schedule a higher data right here if I want to. Schedule more data. Or it could be the other way around, that yeah, the device is using this, but it would actually need to use even more power. So then it probably makes sense to lower the data rate and prioritize differently, because I'm pushing a little bit beyond what you can support. If there's no idea, you should probably say no point. And there's no point in scheduling higher data rate than what you can support. So I mean, if you end up in this situation, you're probably being a little bit too aggressive in your scheduling, because you would need more power than what you actually can find.
Yeah. One question: what about the computational resource in this scheduling? In
the scheduler in the base station, or?
Yeah, the base station.
Yeah, that it is quite a task to do, actually. Because it needs to be very quick and need to look at all the different buffers and take a decision. So it's a fair piece of complexity, actually.
Just maybe addition on the point, isn't this easier to actually do at the application level rather than in the Mac level? Because if you do the scheduling at the application level, the byte stream is already scheduled for according to the priority of the application that is generating the data. So the Mac doesn't have to actually do that much amount of job. It can directly schedule the bytes that are already there, because they're essentially scheduled for the data according to the priority.
Yeah, that's okay.
Sorry to interrupt. Because at least like it looks like a cross-layer scheduling mechanism, because you have to transmit the priority or the scheduling priority from the application, because the application is generating the data to the Mac layer.
But you need to know the status.
Yeah, that's true. I mean, some of the Mac layer needs to know the priority of the different applications.
Yeah.
But if you would put all that decision at the application level, I mean, the application, especially in the downlink, they can sit in completely different servers. It could be a Google server and a voice over IP server in a different country. I mean, how would they coordinate or agree on the priorities?
Now, what I meant by question here, you reduce the power, the transmission power, because from the perspective of the base station, because there is a limitation in the power from not the UE, from the base station. Now, yeah. Is this could happen also in the term of computational process, that the base station, because I read a few papers that that the decoding from the perspective of on the side of the base station could affect I mean the error rate and this stuff. So is it could be considered, or in terms of reducing putting like a constraints in this scenario?
Not 100% sure. I got the question. What was it, the uplink or the downlink?
Uplink.
Uplink. And you wanted the applications in the handset, so to say, to mutually agree on some priorities and then make sure that you have the right mix of data, or?
Maybe I might maybe clarify. It's more the transport layer that would actually do this kind of a job. The transport layer actually gets all the information from the applications, and it can, if there are TCP or for example, there are TCP schedulers who essentially do this kind of job. They set the byte stream in a priority level defined by all the applications in the, for example, in the device. And essentially now you have a byte stream that is already prioritized for the data that has to be transmitted in that particular time step.
The difference is that the channel is here completely in the non-deterministic bits.
Yes.
If you have a deterministic channel, you can subcontract this from whatever higher level protocol you want. But in a random channel like a wireless channel, you have to have the channel information before you can do this. And that's what Stefan's scheduler is doing. It is combining the channel state information coming from the physical layer with all this let's say flow specific information coming from higher layers, right?
Yeah,
and you
so,
cannot, you have to combine them somewhere, right?
So, this is actually my point of it. So you already have the scheduled bits on it. You only schedule the bits at the MAC layer, taking into account channel information. So rest of the scheduled priority that you don't have to actually take into account, the MAC layer essentially doesn't have to take that into account because it is already done by the transport of the application layer.
Yeah, I think in principle you could set up the system like that. If you have two applications that somehow on the transport layer multiplex data according to the priorities or whatever, that you could do, and then you would just have one flow coming down to the MAC layer, and the MAC layer wouldn't see this prioritization. But I think you still need that possibility at the MAC layer. I mean, you could run things that are not using TCP, for example.
Yep,
then you can't rely on some kind of TCP mechanism.
I just wanted to clarify whether the complexity that you actually encountered by taking into account priorities on the MAC layer, is it actually worth it to actually take for the gain that you get by doing the scheduling at the MAC?
Yeah, I think it makes sense. I mean, then in most scheduling instance, maybe they're just data in one of the flows. It would basically fall down to that case in many cases. But yes, I would say it makes sense because the radio channel is varying all the time, and you may have a service that you would like to give at least some resources all the time, so it's not completely starved by some other. And if you can get better quality because of the radio channel or high data equals the radio channel is a little bit better, then you would like to use that as well. So I think it makes sense to have this possibility on the MAC layer as well.
Okay.
But isn't the time scale also completely different? That if you got a TCP time scale and then you got a MAC time scale, here you have at least one order of magnitude difference, right?
Yeah, here we basically talk about decision taking every millisecond or something like that in that time range. And if you think about some, maybe have some ultra low latency, very important, I don't know, some industrial control uplink message from a robot or something like that. That not necessarily on TCP, and that message might be extremely important to get through. So that should be given the highest priority, regardless of what else is going on from that device. So I think the time scale and the radio knowledge, that are two things that speaks in favor of doing things on the MAC layer as well. And that doesn't rule out. It could still be good to do things on high layers as well. So.
Thank you.
Okay. Then we talked about uplink data transmission. And of course, it doesn't make sense to schedule a device in the uplink that doesn't have data to transmit. In the same way, if you have data transmitting the uplink, then you want to be scheduled. So the scheduling request, that is basically the way for the device to tell the network that I have data I would like to be scheduled. So it's basically a flag. A single bit, the device can raise its hand and say, I have data here, please schedule me. And it has the possibility to transmit those scheduling requests once per something, once per 10 milliseconds, whatever you set up your system with. You can configure that. Then you have your own little bit resource in the uplink where you can raise your hand and wave with your flag and say, I have data, please schedule me. And then to handle the different priorities in NR, that was extended by having multiple scheduling request opportunities for different, what we call logical chunks, basically different priorities. You can have one more frequent resource for some of the flows and one more less frequent for other resources. So if I have some data incoming here at one priority class, then I take the next possible opportunity for this priority class, transmit a scheduling request. And then hopefully I will get the scheduling grant back from the network so I can transmit my data. If not, then I transmit the request again the next time I have the chance to do so. This time I got the scheduling grant back, so then I can transmit data on the uplink according to what that grant told me. And typically what the network would schedule you with some reasonable data rate, and in the uplink transmission, hopefully you can include a buffer status report, etc., so that you get more knowledge to the base station and that you later on can do more accurate scheduling. So the scheduling request is basically a reserved resource of one dedicated resource per UE that is connected in the system, where you can wave a flag and say, hey, I have data to transmit. So UEs in RRC connected state, they typically do get the scheduling request resource in uplink, even though you can run without it, and then you have to fall back to random access type of behavior. And this, of course, is something that in some sense adds a little bit to the overall scheme in uplink. You need to send your scheduling request, you need to get the scheduling grant back, and you transmit your data. Unlike the downlink, where data comes to the base station, it immediately can send control signaling and data in one go. So it's a little bit faster in downlink for that reason. Then we also have something called semi-persistent scheduling, or scheduling without a dynamic grant. And the intention with that is to support services with a priori known transmissions. For example, like voice over IP, you know that there will come a voice packet every 20 milliseconds. Or maybe you have some other control loop type application where you know that it's regular transmissions. Then you can set up these transmissions in advance, say that every 20 milliseconds you get this time frequency resource and you're supposed to transmit with this modulation and coding scheme in uplink. And then when such an occasion occurs, if the UE has data to transmit, it transmits it. If it doesn't have anything, then it doesn't transmit. And there are two flavors of this semi-persistent scheduling in uplink here. It just differ a little bit how you configure and activate them. And I don't think it's very important to dig into those details. So it's partially for maybe for non-technical reasons and a little bit of compromise thing in TCP while I have both. But there is a possibility to operate without this scheduling request, scheduling grant scheme you have in dynamic scheduling. So this could also, if this resource occurs very frequently, it would also reduce latency. But main intention is to reduce overhead for periodic type of services. And you can do the same thing in downlink, of course, but then it's more up to the base station just to, you can configure the similar thing there. Okay, battery lifetime. You typically want your battery to last a very long time, which speaks in favor of sitting in RC idle. Drawback is you can't really receive data unless you switch to RC connection. It takes some time. So from a latency perspective, you would like to sit in RC connected all the time, but then of course you drain more battery. So there is a possibility to configure DRX, both in connected and in active states, which means it's discontinuous reception. So it's basically a pattern telling the UE to wake up every something milliseconds and check. So it wakes up here and sees if it's scheduled, receives the data. If it hasn't been scheduled for a while, it goes back to sleep until the next wake up occasion occurs. Then you can run the system typically in the sleep mode. Most of the time the device is sleeping, but still the time between two wake up occasions is not too large, so you still get good latency performance. And then there are some tricks. If you're scheduled during this wake up period here, then you extend your wake up time so that you you should have been inactive for a certain amount of time before you go to sleep and things like that. So there's also some timers to configure. But the basic idea is to sleep and periodically wake up. So maybe you wake up once every 10 milliseconds, once every 20 milliseconds or so, and you sleep 2 milliseconds in between. So that's where you can make the battery to last longer at the expense of a little bit higher latency. So it's again a trade-off, and all the parameters of this is configured by the network. So let's talk a little bit about retransmissions, the last few slides. If you remember this protocol stack here, we had the radio link control, which had a retransmission mechanism, and we also had a Hybrid-ARQ protocol, which also is a retransmission mechanism. And then an obvious question is, why do we have two retransmission mechanisms on top of each other? And then if you do TCP, you have yet another mechanism up in the TCP protocol. And the reason why we have these two is basically a good trade-off between being fast and being reliable. So this Hybrid-ARQ protocol is very, very fast. After each transport block in the downlink, you send back an acknowledgement and you can do retransmission a few milliseconds later. But since you send back the feedback, whether you receive the data correctly or not in the downlink, after each transport block, so you need to send that feedback very frequently, basically after each scaling instance. It could be one or several times per millisecond. And it's just one bit. You just send back that what happened with that single transport block, was it okay or not. It's very difficult to protect a single bit to be very reliable. So there is a certain risk that is, even though you received your data correctly, you sent back a negative acknowledgement. Okay, then you get a useless retransmission. Or a little bit worse, you could have received the data incorrectly, but so you asked for retransmission, but that feedback was corrupted in uplink, so the network thought you received it correctly. So there is a certain risk that you lose some transmissions in this Hybrid-ARQ protocol. It's very fast, but it may do mistakes, like 10 to the -3 or something like that, probability, 10 to the -2, 10 to the -3, depending on configuration. So to fix that, we have the retransmission also on the RLC layer. And here is more like a traditional selective repeat protocol. So when you have transmitted a number of packets after a certain time, or when you request it or so, you can request a status report to see what's missing and retransmit that. And that status report is a little bit more extensive, more bits, and protected using the normal LDPC coding, multiplex together with data and so on. So it's much more reliable, but you can't really afford to request that multiple times per millisecond, maybe more that you requested once per 50 milliseconds or something like that. So that's the reason why we have two. This one is fast, and this one is very reliable. And together they gives you the best of both worlds. The Hybrid-ARQ protocol, this fast protocol, it sits in the MAC layer. It's basically a stop and wait protocol with a number of parallel processes. Here I illustrated 4 of them. You typically have a little bit more than that in reality, but then the figure was too complicated. So what I would do is to send one transport block in the downlink. And then I receive that, I decode it, it was correctly received, so I just feed it up to the higher layers. Then comes next, and while I do that decoding, processing, etc., I can of course transmit a new packet in another Hybrid-ARQ process number 1, the green one. So this one time I happen to have some noise on the channel, so it was received in error. So I try to decode it, I fail, and then I can indicate back to the network that, hey, I missed this one, I couldn't receive it properly, so please retransmit it. And that's done here. And this time I received it properly and I send it up to high layers. And then while I decode this packet 2 in process 1, I can of course have another packet going into the next process and so on, so they run in parallel. So after each transport block, I get 1 bit ACK or NAC back to the base station. And then, of course, there is a certain risk that some of these packets come out of order or out of sequence. I have 1, 3, 4, 5, 2, 6, 7. And depending on whether that is a problem or not, I can optionally configure reordering in the PDCP level. But at least modern TCP dialects that can actually handle this themselves, so you don't have to use it. So that's the basis for the Hybrid-ARQ protocol. It's very, very fast, and after each transmission, you get a 1-bit acknowledgement back. Yes or no, it was good or bad. Then you can actually also configure it for per codebook group retransmissions. If you remember from the first session, one big transport block could be chopped up in multiple code blocks if it's very big. So for very high data rates, maybe just some of the code blocks are affected. Then I can actually, instead of retransmitting everything, I can ask for retransmission of just this missing code block. That's also a way to handle this preemption in the downlink a little bit better. If I had some burst interference, or if someone needed to steal this downlink resource for some other reason, I won't drop the whole transport block. I just affect this one. I can ask for retransmission later on. So that's a possibility you have as well.
Excuse me,
yeah.
Stefan, you said that in uplink there is no need for feedback, as the receiver is in the base station.
Yes.
But is it then in the form of the scheduling grant is then in the form of a please retransmit?
Yes, then the scheduler tells to you that please transmit new data or please retransmit what you sent last time. So then that feedback is in some sense part of the scheduling grant, one could say.
Okay.
But it's not feedback in the sense that the UE knows whether the block was correctly received or not. It's just a command to the UE what it should do. And it could be so that B thinks I don't care about this piece of data, so I just throw it away and say it was okay even if it wasn't. But the UE just transmit what it's told to transmit.
In this ultra-lean approach, so is there a fixed timing relationship now between the uplink the ACNAC sent in uplink for a downlink or scheduled?
No, it's not. And that's something we changed from LT, because in LT, when you receive something in downlink, there was always a fixed time until you sent it in uplink, and then you get the coupling between the two. So in principle, and we'll see that in the next session a little bit, the acknowledgements are scheduled themselves as well. So when I schedule data, I also give the UE information when to transmit the uplink and on what resource. So in essence, that uplink feedback message is also scheduled as part of the downlink assignment. Then we get a little bit into the issue of ARQ codebooks. And that can be interesting and a little bit complicated, but because sometimes we need to feedback multiple acknowledgements at the same time. So let's say that I do carrier aggregation in the downlink. So I have two carriers running in parallel. I receive a transport block each on each of the downlink carriers. And then I need to send the acknowledgement in the uplink, but I just have one uplink carrier. So then I, of course, need to send 2 bits at once in that uplink carrier. Or it could be so that I run TDD, so I have a number of downlink slots and then one uplink slot. Then, of course, when I have this uplink possibility, I need to send acknowledgement for all the downlink occasions. So that is what happens here. I need to collect outcome of multiple decoding attempts for multiple transport blocks and send at one go in the uplink. And of course, the number of bits I need to send back, that depends on how many transport blocks I received in the downlink. And how many resource blocks are received in the transport blocks are received in the downlink, that depends on the scheduling. And there's a certain risk that I miss some of the scheduling assignments. So maybe the base station thought I scheduled 4 transport blocks to that UE, but the UE missed one of them and could just receive 3 of them and just saw 3 of them. And then you must, of course, make sure that the UE reports 4 acknowledgements, including that completely missed transmission, so that the base station knows that, even though it didn't even know about the 4th occasion. So that's the kind of problem you get. Otherwise, if the U would indicate 3 bits because it just heard 3 attempts, but the network expects 4 bits, then you get a mismatch. So that is what you do in the hard codebook, and maybe it gets a little bit clearer in the 2 following pictures, which are the 2 last slides, I think. So we have maybe 2 figures on the same slide, actually. So this is the last slide. Here we have 3 carriers, and they run in parallel. One carrier, I just do no MIMO, nothing, so I have one transport block per slot. And then I have one carrier where I can do MIMO, so kind of up to 2 transport blocks per slot. And then I have one carrier where I have configured the CBG retransmission. So I need to indicate for each of the code blocks or code block groups that I have an error. So I need 4 bits here. And then maybe this is TDD, let's say. So I have all these 4 downlink occasions, and here comes the uplink possibility. There is quite a lot of bits I need to send here. So then I basically get this type of, in each slot it could be up to 7 bits, and 4 slots, so 7 times 4, 28 bits, ARQ or NAC. And it is basically just a bit string I send here, ARQ or NAC, depending on what happened with this data. Here I didn't receive any control signal, so at least from a U perspective, I wasn't scheduled. Then I send NAC for both of these. And here I got some data, so then I transmit ARQ NAC for each of the individual code block groups. And then the same thing here. I receive data here, but just for one of the layers, and so on. And then when my transmission attempts uplink possibility comes, I'll send these 28-bit Hybrid-ARQ report back to the network, and the network knows which of these transmissions that was okay and which I missed, and so on. But that is quite simple. I mean, I just number all the possible transmission events and transmit up a bit string covering all of them. No problem. But let's say I have a large number of carriers, a lot of CBD retransmission, a lot of MIMO, and infrequent reporting for some reason. This bit string can be quite big, or quite many bits. And most of the time, I'm not scheduled at all. All these gray boxes here, they are just NACs because I wasn't scheduled. Doesn't contain much information. So then there's also a possibility for a dynamic codebook, which basically reports only about those events where the network actually scheduled you. I mean, here the network didn't schedule that device, so the network doesn't expect an ARQ NAC for this, and the device wasn't scheduled, so no need to send anything because it was not used. So then you can do dynamic codebook, and let's say you have 7 carriers, and you're just transmitted on some of them. Then you need to know how many transmissions occurred in this slot. So how many ARQ NAC bits am I supposed to generate for this time interval? And then you have in the downlink control information, you have something you call the counter downlink assignment index and the total downlink assignment index. So you see, I just numbered those carriers where I schedule data 0, 1, 2, 3, and 4. And then I send a total number 4 on each of them. And if I start from 0, then the device knows that, okay, I'm expected to receive 5 downlink transmissions, hence I should generate 5 ARQ NAC bits. And in this case, it managed to receive all of them, so that's fine. Later on here, you got the corruption. You see here the number of transmission 11, 12, 13, 14, 15 was missed, and 16. And the total die tells you that you should reach 16 by the end here. And then by looking at these indices, the device could figure out, okay, I must have missed number 15 because I missed the control channel or whatever. And then it could still ensure that the ARQ NAC report it sends back has the right size. But it covers all 17 ARQs here, even though it missed one of the downlink assignments. Then you can just fill in an ARQ there. So that's a way of making sure that we have the same understanding of the number of ARQ and AX on the UE and network side when you transmit them. So that gets a little bit more complicated and messy, but the benefit here is that you need less number of bits than compared to if you would do this with a semi-static codebook. Okay. So time for a break before we dig into control channels, unless you have some immediate questions or thoughts. If so, I hope you stop.
Yeah, I have the same question actually. Now assume that the base station received like 100 requests, scheduling requests from the UE. Then this base station has a specific amount, a limit of computational resource. Now we know there is a relation between decoding and the bit error rate. So because of the timeout at the end each message, it's I'm speaking about the uplink. There is a timeout for each transmission message from the UE. So there is a relationship between the decoding and the bit error rate. So now what you presented, and it's when the base station do the scheduling, take into account like the buffer status error, report the power, but it doesn't take into account the computational resource of the base station itself.
Yeah, that the base station can do, of course. If you know in the base station that I'm out of computational resources or out of memory or whatever, then of course you may take the decision, I don't schedule any UE, or I just schedule a few UEs because I don't have resources to handle more. I need to process this first. So that's up to the base station implementation.
So, but this is not in the specification, yeah?
No, it's not. It's up to your schedule implementation. And the reason, I mean, the general reason of not specifying this type of things, there are many reasons. One is that you want to give the vendors the freedom to choose whatever implementation that makes sense for certain deployment. And also it could be so in the future, I mean, a few years down the road, maybe you want a different scheduling behavior because there's some other service that is very popular or some other thing that the customers ask for. Then you don't want to have to go back to 3D people and redo all the standardization work. It takes time, but rather to have this this freedom to just implement whatever you think makes sense for that scenario. The purpose of specification is to specify as little as possible, but still all the stuff you need to specify in order to get interoperability between the device and the base station.
Thank you.
And the specs are still quite big. So.
This one.
No,
I think that's
Okay, so is it like 15 minutes?
And then yeah, next week they will.
Yeah, 15-minute break for some coffee, and let's reconvene at 20 minutes past.
So 20 minutes.
Control channel.
The HDMI and the micro SD reader, which is something that you shouldn't expect